links to the last 3 exam papers and a copy of the handout that you will have. So this handout here, which is listed here, is an additional handout to the standard formula booklet that you'll have. Standard formula booklet contains standard derivatives, standard integrals, standard trigonometric formulae, other standard mathematics things. You can peruse a copy of it in the Maths Undergraduate Network area on Moodle, so you should familiarize yourself with its contents. In addition, for this unit, you'll be provided with a copy of this handout, which lists the logic laws, the set theory laws, and some of the convergence results. I've got a copy of it here, I'll refer to that a few times. Down here in the exam preparation area, there are solutions to 2016, 2015, an additional past exam paper from 2014, together with solutions, and this is a video which I made last year of me narrating those solutions to the 2014 paper. So just talking through the solutions and making some extra comments as we go. Okay, so there's plenty of material there for you to work with. And don't just focus on those past papers though. Do go back over all the material in the notes and review all the tutorial questions, I would suggest, as so that you have a good thorough coverage of the whole unit. Okay. So I'll start working through my questions here. Oh, flip, I came without my writing paper again. Stick to the bins. So as we go through, please ask any queries that you want, and I'll make various remarks as we go to revise this material. Okay. So in all of the past papers you see, they all follow the same structure. There's a section A and section B. Section A consists of 2 compulsory questions that you have to do, questions 1 and 2. Question 1 here is based on material from my half of the unit. Question 2, you also have to do is based on material from Saeed's half of the unit. That's 2 questions. Every question is worth 20 marks. You need 100 marks in the exam. So those 2 questions carry 40 marks. You then have to do 3 other questions from section B. Then there's a free choice from section B. Okay. Some of them are a mixture of material from mine and Saeed's parts of the exam. Okay. If you do answer more than 5 questions in total, we will mark them all and give you your best combination of marks, subject to the fact that you have to include questions 1 and 2. So okay. So I'll try and give an idea here, as well as kind of the amount of material you should be writing for some of these solutions. Remember always, the key principle is to use your solutions as an opportunity to demonstrate your understanding to the questions asked. Okay. It's a 3-hour exam, so as a rough guide, you've got half an hour for each question, and then an additional half an hour left over for checking or for spending longer on some questions. Okay, so you've got at least half an hour for each of these 5 questions. Okay, so let's have a look at question 1A. The 2017 paper. So question 1A says, here's a sequence defined by this rule. Use the algebra of limits theorem to determine the limit of this sequence. Clearly indicate how you are using the theorem and state any other results that you rely on. Okay. So we want to treat this sequence AN. We're looking for the limit as n goes to infinity of AN. And that, of course, is the limit as n goes to infinity of this expression here, 2n plus 1 over n minus 2. All of that over n cubed plus 2. Now, the instinct we have here is to use the quotient form. Remember, the algebra of limits theorem, which is stated on the exam handout. There it is on the exam handout. You can see that on the Moodle area. You've got clear statements of the linear combinations part, the products part, and the quotients part. Okay. So you'll have that to consult in the exam. So we see here a quotient of things. So we'd like to we'd like to use the quotient part of this. We can maybe multiply out the numerator just to see what's going on. So this is 2n squared, n minus 4n, so minus 3n minus 2. We first might think of applying the quotient form, but of course you can't apply the quotient form and say that this limit is the limit of the top part divided by the limit of the second part, because neither the top nor the bottom have limits. Okay, they're both divergent. Okay, so you need to do some preparation to this before you're able to apply the algebra of limits theorem, and that preparation consists of re-expressing the fraction. Remember, fractions can always be re-expressed in different forms for the same quantity. So what we're going to do here is divide above and below by n cubed. Dividing the denominator by n cubed produces this denominator. Dividing the numerator by n cubed provides 2 over n minus 3 over n squared minus 2 over n cubed. So a little comment there, dividing top and bottom by n cubed to prepare for the algebra of limits theorem. It's no harm just giving a little commentary and justification for what you're doing. We're dividing the top and bottom by n cubed as a preparation for doing the algebra of limits. Okay, so we can now say that this limit is the quotient of the limits. So it is the limit of the top part. We won't break it down any further for the moment. Divided by the limit of the bottom part. We will see that this will turn out to be justified because we will see that both of these limits exist in a moment. Okay. Well, we need a justification for this. So this is the quotient form. This is the quotient form of the algebra of limits theorem. Okay. Trying to be accurate and quote each relevant part as we go. But then both the top and bottom are limits of linear combinations of simpler sequences. Okay. You've either got a constant or you've got a constant multiple of one of these 1 over n type sequences. Okay. So we can break those down then using the algebra of limits theorem again, but this time for linear combinations. Yeah. Okay. So this will be 2 times the limit of 1 over n. I'll suppress writing the subscripts here because it's understood what they should be. Minus 2 times the limit of 1 over n cubed. Down here we've got the constant 1 plus 2 times the limit of 1 over n. The justification for that is the linear combinations form of the algebra of limits. Okay. The linearity part of the theorem. Theorem, what I mean is clear, because it's the algebra of limits theorem I was referring to earlier. And now finally we've got the whole thing expressed as the limits of individual standard sequences. And we can appeal to the known fact of how these sequences behave. Well, this is going to be 0 over 1, since 1 over n to the a converges to 0 for all a bigger than 0. Okay. Whenever a is positive, as it is in each, whenever the exponent on n is positive here in the denominator, as a equals 1, a equals 2, a equals 3, a equals 3, all of these converge to 0. As n goes to infinity, I guess we should say. So it's 2 times 0 minus 3 times 0 minus 2 times 0, so it's 0 in the numerator, but we got that constant 1. Okay. So overall, the whole thing is 0. But you can see what's being assessed there, okay? The things that the marks are going for, you just writing down the whole thing as limit 0 at the start wouldn't attract full marks at all, okay? Because the question has asked you to show how the algebra of limits theorem is working and to mention any other relevant results that you're relying on, okay? So each of these references, maybe this little comment about the manipulation you're doing, the reference to the quotient form, the reference to the linearity form, and the reference to this standard result about these known sequences. These are the justifications and explanations that the marks are doing. Okay? And so that we can see that happening in your calculation, and you give just a brief indication of what justifies each set. Okay? Is that okay? Any related queries off that? So when I'm marking this, if I'm going to be awarding full marks, I'll be looking for a good, clear indication of each of the different parts being used, a good, clear explanation referring to a standard result, and showing some good development. Okay, and don't leave out the limit sign operator. Many people in marking the class tests, I've noticed many people are a bit sloppy in omitting the limit operator sometimes. It's a crucial device. Okay. Okay, so that's our question 1A. Part B then is an application to a series. Look at part B here. Can we just keep the talk down a bit? It's quite, everybody can hear it. Okay, so question 1B. Consider this series here, the sum of the terms Pn. Pn is defined as 2 over n factorial. Use an appropriate convergence test to determine if this is a convergent series. Okay, so remember, for series, we had a whole collection of convergence tests. They are listed in the handout, so you'll have the statements of these convergence tests available to you. There's many of them. There's the general term test, geometric series test, integral test, comparison tests, alternating series tests, ratio tests, root tests. Okay? There's many different ones to choose from. So you don't have to worry about recalling the precise individual details of each one, because you've got them in the handout, but you do have to be familiar with them. And especially when you're confronted with a situation here, I mean, you're not given any further direction, you just say, told use a test. Okay? So how do we do this? Okay, so we're considering the sum of 2 over n factorial, n equals 1, 2. Well, it's the ratio test that's going to be useful here. Okay? Because of the use of factorials there, when we examine the ratio of consecutive terms, we'll be taking a ratio of nearby, kind of neighboring factorials, and then most of the terms are going to cancel. So due to the use of n factorial, it seems the ratio test may work. Maybe it would. So you can look at the statement of the ratio test. It says take the limit of the ratio of consecutive terms, one term divided by the one previous. Okay, so you're looking at how the terms change from one to the next. What proportion is each term of the one that preceded it? So we look at the limit as n goes to infinity, bn plus 1 divided by bn. Okay, the test is quoted in the handout. It's the limit of an over an plus 1 over an. Okay. So this is the limit of the sequence of ratios. Okay, so what is bn plus 1? Bn plus 1 is 2 over n plus 1 factorial. And that's divided by bn, which is 2 over n factorial. And just working with your fractions accurately, there's a factor of 2 in the numerator and denominator of the overall fraction. And then you've got a denominator in the numerator and a denominator in the denominator. So this will come to n factorial over n plus 1. Okay, just by manipulating the fraction. And then we call on the definition of the factorial. Remember, the factorial is the product of all the integers starting with the named 1, all the integers counting down to 1. Okay. But of course, so all the factors contained in the top are also present in the bottom. And the bottom contains one more factor, namely n plus 1. Yeah. So this is going to cancel to just be the limit as n goes to infinity of 1 over n plus 1. Okay. Please. So we can say all other factors cancel due to definition of the factorial. Just some kind of little comment to indicate to the reader what has happened. You don't necessarily have to write out, expand the factorials as n times n minus 1 times n minus 2. I mean, you could do that. That's a way to indicate it, but just an appropriate comment like that can do the job just as well. Okay, so then we're taking the limit of that quantity, 1 over n plus 1. That's a fairly standard sequence. We can say that the limit of that is 0. Okay. Can we just keep the chat down, please? Everybody in the whole room can hear it. I can hear it very loud. Thank you. Okay, so we've reached this intermediate stage. We've got a limit of the sequence of ratios to be 0. So this is our L equals the L named in the series, named in the test. And we draw our conclusions about the nature of the series based on the value of L. So since 0 is less than or equal to L is strictly less than 1, that's the criteria. And that's certainly true because L is equal to 0. And the ratio test says that the series sum of 2 over n factorial converges. Okay, so that's the conclusion. Doesn't tell you what it converges to, doesn't give you any of that kind of information, but it just tells you that it does converge. And it seems reasonable because what this limit means is that as you look out along the sequence, each term is an ever decreasing ratio of the previous term. And by ever decreasing ratio, we mean actually the scale, the proportion that each term is of the previous one, that proportion is converging to 0 as you go further and further out along this series. The first term of the series is the quantity 1. Is it 1 or no? 2 over 1 factorial 2. Okay. It's not too big, but then you get smaller and smaller and smaller and smaller proportion of 2's are the terms, and those are all identical. Okay. So it seems like a reasonable conclusion. The terms of the series are converging to 0 fairly fast. Any related questions or queries off of that? Is that okay? Okay. A good, clear demonstration of the workings of the test, and a nice, clear conclusion at the end. Okay? Nice, clear conclusion statement that answers the question asked at the end. Part C here is about some work with the derivative. It's just simply find the first and second derivatives of a function. We're clearly stating any results about differentiation that rule out. Okay. So we're considering the function f, which is defined by this formula here. F of x is x squared times the cosine of 2x. Okay, and the question wants its first derivative and its second. Well, what do we think when we try to take the first derivative of that? What we recognize, before you launch into it and do anything, you recognize that it's a product of two non-trivial functions of x, the x squared part and the cosine 2x. So it's at least going to need the product. And then one of the functions is a composition, cosine of 2 times x. So for that part, we're going to need to use the chain rule. So we could say using, put a little comment here, applying the product rule, and then chain rule for the cosine 2x factor. Okay, so just a little lead-in comment and explanation of what the calculation is going to be. You can apply the product rule and the chain rule for the cosine 2x factor. Okay. Very straightforward. You can find statements of the product rule and the chain rule for reference in the standard formula handbook. Okay, so don't be worried about misremembering any of those. You just have to be, familiar with it to recognize when it's needed. So what we're going to have for this is, so hold the x squared the same, then multiply by the derivative of cosine 2x. The derivative, and here we want to use the chain rule for working out the derivative of cosine 2x. That's going to be minus the sine 2x by an extra factor of 2. Okay, that's the operation of the chain rule. Differentiate the outer function to get minus sine. Evaluated at the very same argument. So the sine is evaluated at the very same argument it was before, and then you multiply by the derivative of the inner function. Inner function here is 2x, so it has derivative of 2. That's the first part of the product rule. The second part is to keep the cosine 2x factor the same, and then to multiply by the derivative of the other factor, which is x squared, which differentiates to 2x. So tidying up there, we can maybe see a common factor of 2 times x in each of these. So we can maybe factorize it, make it a little bit easier. 2 times x into minus x times the sine of 2x plus cosine of 2x. You don't necessarily have to factorize it like that, but my instinct when you see these things. And then you're asked for the second derivative. So what you would definitely want to make clear that you understand here is the definition of a second derivative. The definition of a second derivative is the derivative of the derivative. So you should indicate that. Shows you have a clear understanding of what the second derivative is. And again, I don't think we need any new principles. It's again just going to be applying product rule and the chain rule as appropriate. But the way we've got it organized, we're going to need a couple of iterations of the product rule. Okay? So again, applying the product rule, product and chain rules, repeatedly, let's just say. Now you have to make a judgment when you're working through these, whether you kind of micro-reference each and every individual separate application of the product rule and the chain rule with comments on the side. I don't necessarily have to see that to award you full marks. I just need to see you making enough explanation to indicate your understanding. And as long as it's clear in the algebra as it works its way down, you know, if you just declare there, I'm going to be applying the product rule repeatedly and the chain rule repeatedly, and if it's done correctly, I'll award full marks. I don't necessarily have to see like each individual reference of the application of each product rule. Okay. Okay, so what are we talking about here when we say product rule and chain rule? So when you look at the top level of this thing, you see the top level is a product of that 2 times x times that bracket. So you apply the product rule to that. So we hold the, I'll just drop down to the left-hand side here. We've got 2 times x multiplied by the derivative of the thing in the bracket, which I may as well do now. And the derivative of the thing in the bracket, well, the thing in the bracket is the sum, so I can use linearity. Oh, so that's a new product. So linearity, I'll add in as one of the properties of the derivative. Because when I'm taking the derivative of that, that large bracket, it's a sum of 2 things. So I'm going to take the derivative of the first one plus the derivative of the second one. So that's the application of the linearity. The derivative of this first one itself requires the product rule again, because it's the product of 2 functions of x. So it's going to be minus x times the derivative of sine 2x, which is cosine 2x by 2. And complete that application of the product rule. It's going to be minus sine 2x by the derivative of x, but the derivative of x is just 1. So that's the derivative of that minus x sine 2x part, I think. And then plus the derivative of the cosine 2x. So that'd be minus the sine 2x times 2. Close that bracket. Now we're back to, it's almost like you're executing computer code here. We went into a loop to do the first product rule, then we went into a second loop to do the inner product rule. Now we're popped back out to the middle of our first product rule. So we have 2x times the derivative of the thing in the large bracket. And then we have the large bracket, the original large bracket, minus x sine 2x cosine 2x times the derivative of the first factor, 2x, but that has derivative 2. Okay, so I think I've indicated all the individual steps. The only thing then to do would be just to tidy the thing up. How should I tidy this up? Well, there's cosines and sines, so maybe take out those factors. You got cosine 2x, and that's multiplying a polynomial. There's an x squared term here, so it's 2, 4, minus, so it's minus 4x squared. There's another cosine 2x down here, plus 2. And then there's a sine 2x, and that's probably multiplying something. It's multiplying minus 2x, minus 2, minus 2x again. We've got 2 copies of minus 2x. That's going to be minus 4x. Hang on a minute. Minus 2x sine x, minus 2x sine x. Well, that's minus 4x sine 2x. So no. It's minus 2, minus 2, minus 4. So it's minus 8x. Is that correct? Just want to triple check that. Minus 2x, minus 4x, minus 6x, and minus 2x again. Minus 8x. Okay. There's my second derivative of that. Okay, any related questions from that? Okay. So the final part of question 1, part D, is going back to something we did only last week. So here you're given a permutation. The permutation is a bijective function. Keep the chapter down. A permutation is a bijective function on a finite set of objects to itself. The fact that this sigma is in the symmetric group S7, so that indicates it's a bijective function on the set on a set of 7 objects. And the convention is they're just labeled 1, 2, 3 through 7. And it's given by the following composition of cycles. So this collection of brackets here, each bracket is a cycle. It's referring to the permutation of on a smaller set of elements, where within each bracket, the operation of the function described by each bracket is to send each object to the next one to the right, and the one at the end of the bracket gets sent to the previous one. That's what each individual bracket is doing. The overall expression is a composition of these. So it's like a composition of functions. The first bracket, after the second bracket, after the third, after the next, after the next. So it's the one on the right-hand side that's applied first. You see these composition of functions, unless it's specifically indicated otherwise, the convention is the one on the right-hand side is the one that's applied first. Then the one to its left, then the one to its left. So we have to find, now, yeah, this isn't the nicest kind of composition because these different functions interfere, these different functions operate on some of the same elements, okay? You see the same element appearing in multiple cycles, okay? Instead, we get a much clearer picture of what the permutation is doing when we see its expression as a composition of disjoint cycles. One cycle operating on a certain set of elements, another cycle operating on a completely different set of elements, not touching the ones belonging to the first cycle, and maybe further disjoint cycles as well. Okay. So sigma is equal to, let's just write down what it is, 2, 3, 1, 7, 3, 5, 6, 4, 2, 4, 1, 6, 5. So I'll just make a little comment here by applying the composition of cycles. We discover, let's just say we discovered the disjoint cycles. Discover the disjoint cycles within sigma. Now you've got a certain amount of flexibility here. Remember, the numbers carry no meaning apart from just serving as distinct labels for the objects. So why not start at 5? No reason not to. Well, it'll be right at the end of that. So 5 is going to appear in one of the disjoint cycles. So something is going to be to the right of it. 5 will get sent to something by sigma. To work out what that is, you have to apply each of the functions in turn. Apply the first one to 5, then apply the next one to the image of 5 under the first one, then apply the third one to the image of 5 under the composition of the first two. But you can do it just by reading carefully from the right. So the first cycle sends 5 to 1. So 1 is the output from the first cycle. What does the second cycle do to 1? Well, 1 isn't mentioned in the second cycle. And the convention is if an element isn't mentioned in the cycle, it's left fixed by that cycle. So the intermediate value of 1, because 5 was sent to 1, the intermediate value of 1 is left fixed at 1. So again, the intermediate value of 1 gets passed on to the third cycle. It's still not mentioned. So 1 is sent to 1 by that third cycle. The intermediate value of 1 is passed on to the next cycle. This next cycle does act on 1, and it sends 1 to 7. So 7 is the penultimate intermediate value. That 7 gets passed on to the final cycle. That doesn't mention 7, so that sends 7 to 7. So overall, 5 gets sent to 7. Okay, so 7 is the image of 5. So 7 is going to be appearing to the right of 5 in this partially completed disjoint cycle. Yeah. So then we ask ourselves, well, what does 7 get sent? 7 must get sent to 7. 7 is left fixed, left fixed, left fixed. 7 gets sent to 1, and 1 is left fixed. So overall, 7 gets sent to 1. You just keep playing this game. At some point, you'll notice that your element here gets sent back to the starting element in the cycle. At that point, you'll close off the cycle. And if you haven't exhausted all the elements yet, you'll begin another disjoint cycle, beginning with one of the unused elements. So what's to the right of 1? What happens to 1? Well, 1 gets sent to 6 by the first one. The second one fixes 6. The third one sends 6 to 4. And then that intermediate value of 4 is left fixed by the remaining cycle. So overall, 1 gets sent to 4. Then what happens to 4? 4 is left fixed. 4 gets sent to 2. The intermediate value of 2 is left fixed, and then 2 gets sent to 3. So this cycle is turning out to be quite long. Then what happens to 3? 3 is left fixed, it's left fixed. 3 gets sent to 5, and 5 is left fixed, and 5 is left. So 3 gets sent to 5, and I might initially go to write down 5 here, but then I notice 5 is the beginning element of the cycle. So that marks the closure of that cycle. Within sigma, it has the structure that sigma cyclically permutes these 5 elements around each other. So it's 5 to 7, 7 to 1, 1 to 4, 4 to 3, and 3 to 4. So there will be a cycle then, so you just have to look at the ones that have been listed here. So 2 hasn't been listed. So there's going to be another disjoint cycle featuring 2. You continue that in the same way. 2 is left fixed, 2 gets sent to 4, 4 gets sent to 3, 3 is left fixed, and 3 gets sent to 2. So 2 gets sent to 2, 2 gets sent to itself by sigma. So 2 is on its own in a little trivial cycle. Sigma sends 2 to 2. The only one that hasn't been mentioned yet is 6, and that is the only one that hasn't been mentioned. So 6 must, you kind of know automatically then, because this thing is going to be a bijection, 1-to-1 and onto function. 6 is the only argument left. It's also the only thing left as a value for sigma. So 6 is going to have to be sent to itself. You can confirm that by checking here. 6 gets sent to 5, 5 is left fixed, 5 returns to 6, 6 is left fixed, 6 is So we get that sigma, the structure of sigma is 1 5 cycle and 2 1 cycle. Sigma has the structure, it's called the cycle type, but it's called as the structure of 1 5 cycle and 2 1 cycles. Unfortunately for this kind of answer, there isn't, I mean, I spoke a lot there, I narrated what I was doing, there isn't a huge amount of justification you do along the way. I wouldn't require people to kind of write out that whole explanation. I think this is enough. You can just indicate what you're going to do. You're going to apply this composition of cycles and discover the disjoint cycles. That's enough. And if you get it to this kind of thing, you could also indicate that by convention the trivial cycles can be dropped. Because it's understood that the action of this cycle is to fix 2 and 6, because 2 and 6 aren't mentioned. Okay. So specifying separately the trivial 1 cycles isn't necessary. No, it doesn't, because they're disjoint. Yeah, so that's also a good point. The compositions of these, we can reorder these cycles, reorder the 3 cycles there, however we wish. That's fine. Of course, you can't reorder these ones in sigma because they're not disjoint. Disjoint cycles you can do in any order because they don't interfere with each other. Like this hand does something over here, this hand does something over here. Doesn't matter which click you do first, the overall effect is the same if you do both. But if you're moving objects with your hands, but you've got fingers from both hands on the same object, it does make a difference which one goes first and which one goes second, because they're operating on the same set of or some subset of the same element. Equally well, you can cyclically permute these things as well. So you might have chosen to start at 4, in which case you would have discovered this as 4, 3, 5, 7, 1. So there are multiple ways. Well, there are 5 different ways of writing that. Okay, choosing each of them as the starting point. Each one is equally good as any of them. Is that okay, so? Any other related questions? Off with that. Okay, pushing on then. I'll continue this tomorrow as well, but I should have time to do another little part now. So that's all of question 1. So then you may opt to do, or you may have opted to do question 3. So this is a question, there's some more detailed questions about sequences of series. In 3 part A, you're asked to show that the sequence is a decreasing sequence. So I would say we can show that an, which is n over 2 to the n, is decreasing by comparing the ratio, sorry about my writing there, comparing the ratio an plus 1 over an by comparing this to 1. By comparing it, I mean working out if this ratio is bigger than or less than 1. Okay? So if the ratio is bigger than 1, it means the top is bigger than the bottom. If the ratio is less than 1, it means the bottom is bigger than the top. With the understanding that these things are always non-negative, strictly positive. So I can perform that. Could also equally well look at the difference, an plus 1 minus an, but that you compare that to 0. Looking at a difference, it's whether it goes either side of 0 that tells you which one is the bigger term. So I just choose to go for ratios here, but you could equally well do it with differences, I think. So the an plus 1 is n plus 1 to the power of 2 to the n plus 1. And the an is n divided by 2 to the n. So we got multiple factors here above and below the line. Of course, you got a load of 2's in the denominator up here and a load of 2's in the denominator down there. Okay? They will all cancel with each other, just kind of like in the factorial thing. They all cancel with each other except this one up here is 1 more 2. So that 2 will remain. It will remain in the denominator position there. So let's drop it down and say it's a half times n plus 1 over n. And in fact, it's slightly more convenient or emphasizes what's going on if you write n plus 1 over n, if you separate it into its 2 parts, that's going to be 1 plus 1 over n. Now, how does this quantity compare to 1? That's the question. How does this quantity compare to 1? Well, when n is equal to 1, it's 1 plus 1. 2.5, so it's equal to 1. So this thing is equal to 1 for n equals 1. But for every other value of n, it's 1 plus a small bit. So it's a little bit bigger than 1, but not bigger than 2. Well, then you're taking a half, so that's going to bring it back down below 1. So it's strictly less than 1 for n bigger than or equal to 2. So this is telling us that the first two elements of the sequence are the same. A1 is equal to A2, because the ratio of A2 over A1 is equal to 1. But after that, how does A3 compare to A2? Well, A3 divided by A2 is less than 1. How does A4 compare to A3? A4 divided by A3 is less than 1. Okay? So that shows that this must be a decreasing sequence. So we can say for all n bigger than or equal to 2, we've got an plus 1 over an less than 1. And that's true if and only if an plus 1 is strictly less than 1. I.e. the sequence is decreasing. Is that clear? So here, i.e. A2 is equal to A1. But after that, the sequence is a decreasing sequence. So we should call this a decreasing sequence. Okay, I'll continue with doing these solutions tomorrow. Please come along then and we'll discuss these some more, and I can answer any questions or queries about anything, any related topic as we go along. Okay?